now. Okay, you have the word.
Thank you, Leo. Can you all hear me? So I hope if Leo can hear me, that you can also hear me.
Sure.
So thank you for the opportunity to explain some of my work. The title is, of course, going to be on precipitation in steels, and I use a technique which is neutron scattering for that. Maybe to introduce myself a bit here at TU Delft. So the outline of the talk will be an introduction, then some explanation on neutron scattering, then an introduction on precipitation, and then how we combine the two to learn something useful for steels. So I have different research interests. Typically, it's a combination of materials and advanced radiation techniques, specifically neutrons and synchrotron X-rays. This is an example of the work we have been doing with synchrotron radiation. It's specifically on what you can learn from microbeam diffraction. And this work started together with Eric Offerman, who you all know in this community, on the phase transformation in carbon steels from the austenite to ferrite transition, but we continued with various other transitions like austenite to martensite in trip steels and in more aging steels. And we have looked at solidification, where you go from a liquid phase to a solid phase. So you can also follow how the solid phase forms and grows inside the liquid. And finally, we've also done some phase transformations in electrode materials for lithium batteries. So the power of that is all that you can do in situ studies and time resolved information without having to cut open your system. So another activity we have been working on is self-healing materials. So those are also metals, iron-based metals. And at high temperatures under load, over time, you can make damage that occurs at the grain boundaries that are under load. And we have investigated different strategies to try to extend the lifetime by filling up those damaged sites by precipitation. And one of the ways we have studied this is by X-ray tomography. And this is extremely powerful. Here you can see an example of gold and iron alloys. So it's 1% gold in an iron matrix. So if we, at high temperature, 550 degrees, put it under load, you see that in red, you see where the cavities start to form over time. And in green, you can then see how gold sort of fills up those empty spaces and thereby extending the lifetime. Gold will never be used in a creep steel, but we later found out that you can also do this with tungsten. And a last topic that I work on is magnetic materials, and then specifically magnetocaloric materials. And they are based on the concept which has been demonstrated 100 years ago, that if you have a magnetic material and you put it in a magnetic field, what then happens is that all the spins are aligned. So if you do this movement under adiabatic conditions, that there's no energy transfer, then you will see that because the total entropy is conserved, if you then reduce the magnetic entropy, it has to go somewhere, which means that the lattice will heat up. If you then wait until it gets the same temperature, if you then pull it out of the magnetic field, you'll see that the sample is cooling. So you can actually build this in a cycle and make a magnetic refrigerator. Now, this concept is already very old, as I told you, and it's still the standard way to go to ultra low temperatures, down to 100 picokelvin. That's all very exotic, but you nowadays also have materials that have a big effect around room temperature, and then it becomes interesting to build this into alternative magnetic cooling devices. And our interest is to then learn how this works. In the example over here, we have the materials that we work on. So you can see they're manganese, iron, phosphor, silicon based. So there are no scarce materials in it. And they work around room temperature. So you can actually build this into a refrigeration cycle and do the cooling. And if we then want to understand how that works, you need to know what the spins do. So we use neutron diffraction to measure the individual spin sizes and directions. And you can see that the phase transition actually has some jumps in the lattice parameters, which indicate that there's actually latent heat in a magnetic transition. And that is one of the reasons why these materials work so well. So this is general background. If we then go to the topic of today, one of the ways to improve the properties of steels is to introduce nanoscale precipitates. And this is already a very old trick that is used a lot. If you go to textbooks, this is one example. If you have aluminium with copper, you can really see that for certain concentrations, you can design the precipitates that form. Depending on the heat treatment that you apply, you get precipitates of a certain density and a certain size, and you can play with this to get the properties you want. You see that the precipitates on a nanoscale segregate into the material, both in the bulk and on the grain boundaries, and this has specific consequences that you can have a strengthening effect. Now, I have mainly been focusing on precipitation in iron-based systems. And in all these cases, precipitation process itself typically has two stages. You first go from metastable clusters into stable particles on a nanoscale. That step is called nucleation. So you form nanoscale stable particles inside the bulk of a material. So that happens on a very small scale. It typically goes fast and it's going to happen inside the material. So it's typically not easy to study. And the second step is then once it has formed, it will want to grow until you have reached the equilibrium phase fraction of this secondary phase. And so we are continuously looking for ways to investigate what happens during these steps to have efficient information on these particular steps that are important for the properties of the final steel. So if you then look for nanoscale probes, there is a limited number of options. So the options that we are investigating is small angle neutron scattering and small angle X-ray scattering. But these complement the more traditional and more widely used techniques, which are, of course, transmission-electron microscopy, which is a standard approach to learn something about the nanoscale particles, and more recently, the atom probe tomography. And both of these techniques are very powerful and are the standard approach to see what precipitates are actually formed in the final product. But it's very difficult to get time-dependent information on how you get to these final properties. So that's where these in-situ techniques like neutron scattering and X-ray scattering can come into play and give some additional feedback on how the process works in a kinetic sense. So some properties of these nanoscale probes. If we look at small angle neutron scattering, I will later on explain how it works. The basic advantages are that you have a non-destructive technique, which is in situ, and you can then do time-resolved measurements. And the other thing is that you probe a relatively big sample volume, which is typically 5 millimeters times 5 millimeters, and a sample thickness of about 1 millimeter. If you go to X-rays in metals, typically you need thinner samples because you lose the penetration depth is often limited, but it has a very high flux and you can get very good time resolution. So if we compare that to TEM, then TEM has a fantastic resolution, typically up to atomic scale. And you can really get the shape and internal structure of the these secondary particles on a nanoscale with very high resolution. If you look at atom probe, they give fantastic information on the chemical composition of these secondary particles, whether they're internal gradients in composition and so on. So my conclusion is that quite often there's a lot to be gained by combining some of these techniques. So quite often, if we do neutron scattering, we always combine it with at least one of the two other more conventional techniques like transmission-electron microscopy and or atom probe. And the combined thing gives then a lot of extra information. So something about neutrons. We all know that neutrons are part of the core of all the atoms. So the core is composed of neutrons and protons. And around it, we typically have all the clouds, the orbits of the electrons. But with some effort, we can liberate these neutrons either in a nuclear reactor or in accelerator-based facilities where we liberate the neutrons out of the nucleus of an atom. And we can actually make beams out of this and shoot this at a sample and see what happens. Now, an important property is that the neutron is both a particle and a wave. And this is something very basic in quantum mechanics, which we also have for electrons and for even for photons. Photons are the quantized electromagnetic waves. So for neutrons, it's quite obvious that we can see this as a particle because it has a mass, but it's not so obvious that this is actually a wave. And you can see this by doing interference experiments, and then you can really see the wave character. Of course, for photons, like the electromagnetic waves, there it's the opposite. It's quite obvious that it's a wave. We all know the properties of light, but it's maybe less obvious that this is a particle. If you have a modern camera, you can actually count light particles one by one. So what are the properties? The basic property of a neutron is that it does not have a charge. So that in contrast to the protons and the electrons, which are always balanced if it's a neutral atom, it does have a spin. So it's a magnetic particle. It's a spin 1/2 particle, and the mass is very similar to the proton. Not equal, but similar. Now, this property that the particle that the neutron is both a particle and a wave directly comes in with all the mathematical properties. So the basic thing that you need to remember is that if we have the momentum of the neutron, then classically, according to Newton, this is simply the mass times the velocity. So this is the particle picture. But at the same time, if we use the wave description, then it's Planck's constant divided by 2 pi times the wave factor. And the wave factor is 2 pi over the wavelength. So this is a spatial frequency. And then after that, all the properties derive from these two notions that these are coupled, that it has both a particle character and a wave character. Now, to get a feel for how neutrons interact with things, we can compare it to what X-rays do. So this is an old-fashioned camera, not a digital camera, but one where you actually transport film. If you then put it in a neutron beam, then you see that essentially all the metal parts, like the aluminium casing, is transparent per neutrons, but there is you lose a lot of intensity when you when you meet the plastic parts. So it interacts strongly with hydrogen, and that means that the transmission is low for hydrogen-containing parts. And for X-rays, it's the opposite, that it's difficult to penetrate the metal, but the plastic with all the light elements, which contain low amounts of electrons, it's much easier to penetrate. So this is to get a feel for how neutrons interact. They interact with the nuclei and not with the electrons, and that's because they don't have a charge. So the X-rays actually interact with the electrons, and therefore you have a stronger interaction for heavier elements. Yeah, so if you look at the interaction, so the X-rays interact with the electrons, so they can be absorbed and then, for instance, kick out an electron out of the orbit, or be scattered from the electrons in the atom. Neutrons scatter from the core and not from the electrons. And that means that also where the interaction with the X-rays is very systematic, the more electrons you have in the atom, the stronger the scattering. For neutrons, you interact for very specific elements very strongly and for others very weakly. So this is difficult to predict from first principles, but you can look it up in tables and you can see which elements you're most sensitive to. So here's an example. What is the chance of scattering, the scattering length compared to the atomic number? So for electrons, this goes up continuously. And for neutrons, it goes all over the place. You can even see that different isotopes, which have the same number of protons, but different numbers of neutrons in the core, actually can have very different scattering properties. So that we can make use of in specific experiments, that you are very sensitive to specific elements. So for instance, this is used a lot in the study of lithium in battery materials. So where can you do neutron experiments? So you always need relatively large facilities to liberate the neutrons and make intense beams out of them. So in the world, there are somewhere in between 20 and 30 places where you can do these sort of things, and they vary in strength. Within Europe, the classical high flux facilities are ILL in Grenoble in France and ICES in the UK. And we are currently waiting for the new European spallation source, which is in Lund in Sweden, which should start up within a few years. But you can see that also in other continents, there are various places where you have access. So we are also based at a source. So this is a relatively weak source with 2 megawatt, but we have also competitive instruments to do research on various different instruments. So we also do have our own small angular neutron scattering instrument, which is currently under the last testing stage, and some diffractometer and some various other neutron instruments. So we recently had an upgrade where we had a cold source, so that now makes it possible to slow down the neutrons that are generated in the reactor and make them useful for the technique that I will describe today. So the basic principle that we use is interference of waves. This was first, how this works was first introduced by Huygens, but it took a long time before it was accepted that how light actually causes interference. And it actually experimentally was only really demonstrated very elegantly by this double slit experiment by Young. Quite a bit later in 1801 with visible light. The basic idea is that you have a source that is in phase at these 2 slits. So that means that you have to position the original source, for instance, the light of the sun, in such a way symmetrically that both of these phases, both of these point sources within this plane are in phase and then generate some interference pattern on some screen at a certain distance. And what you see is that at certain distances you have a very intense, high intensity, and in between you have a very low intensity. And this can be interpreted in terms of phase differences of the waves that arrive from these 2 slits, and that can be interpreted in an integer difference of the phase, or half difference of the phase. So an integer difference will lead to constructive interference. All these waves will add up, and in the other case, they will just die out because they are each time out of phase at these particular orientations. And this process typically critically depends on the distances and the wavelength that you use. Now, this was demonstrated for light already more than 200 years ago, and for electrons and neutrons, because we demonstrated that it's both a particle and a wave. This should also be possible, but it was demonstrated much more recently, only in 59 and 88. So what we do in a neutron scattering experiment with small angle scattering is that we investigate elastic scattering of neutrons on some scattering object. And essentially what you can then do is mathematically describe this as the momentum going in, the momentum going out, and some momentum transfer. And this difference between the momentum that goes in and goes out is the scattering angle to theta. Now, we can use momentum and energy conservation. This is an elastic scattering process, so there's no momentum transfer. So that means that the energy of the neutron that comes in is the same as the energy that goes out. And for the momentum, we also have momentum conservation, but this is a vectorial process. So we can have this balance that the momentum transfer is then related to the difference in the two momenta. And that can be translated into a wave vector, which is this spatial frequency k. And the difference is now translated in what is called the wave vector transfer. And that is now this difference. Now, vectorially, you can also make this what is called the scattering triangle, which is all the same as what you have in, for instance, X-ray diffraction. So you can now, by only looking at the top triangle, construct this relation for the wave vector transfer, the wavelength, and the scattering angle, or half the scattering angle, because this total scattering angle is 2 theta. The Bragg angle, this is called in diffraction. Now, the reason that we introduce Q is that this is more generic, because then the results do not depend on what wavelengths you actually use. So in scattering process, you have a scattering angle and you use a specific wavelength. So if you define Q, then it's independent of what wavelengths you've used. So this is terminology. What does a SONS experiment actually measure? So if we put a sample inside the beam, which has inhomogeneities of the size between 1 nanometer and 100 nanometers, you will see an interference pattern at the back, which is caused by the particles that are embedded in the sample. And there are two possible sources of scattering. The first is that the particle has a different chemistry than the matrix. Then the composition of nuclei will be different, and that difference will result in contrast, which is the source of this scattering. You can also have a difference in magnetization, and because the neutron is a magnetic particle, it also interacts with the magnetism. So if there's a difference in the magnetization between the matrix and the precipitate, then that will also cause magnetic scattering. The thing is now that magnetic scattering is anisotropic. So if you completely magnetize your material, that all the spins are aligned, you will see that the scattering pattern actually has this funny 8 shape. And that is because the magnetic scattering only occurs when there is a component of the scattering vector that is perpendicular with respect to the spins. So if the scattering takes place in this plane where Q is along the magnetic moment, then you don't see any magnetic scattering, and perpendicular you have the strongest scattering. So this is actually a way to separate the two contributions and make it possible to analyze what you measure. Yeah, so mathematically, what is it that you actually scatter from? That is the contrast in what is called the scattering length density. So this B is the coherent scattering length, is something you can look up in tables, and N is the density, atomic density of these different elements. And so if there's a difference in chemical composition or in density, then this will be a source of scattering. Magnetically, there is a proportionality factor, and then you have the difference in magnetization, and that will be angular dependent. And this, if you align everything, then it will depend on this angle between the scattering vector and the magnetization. And the magnetization is a moment density, so that's the size of the moments and the atomic density. Now, that is the scattering, let's say, how strongly you scatter. Now, it also gives information, what we want to get out finally is a size distribution from the scattering in a nanoscale range. And the way to do this is to calculate the scattered intensity for different shapes. So you can show that if you have this scattering power for this scattering length density, that the intensity goes with the square root of the form factor, and the form factor is the Fourier transform of this scattering length density. So to illustrate, if you have a sphere, then the scattering pattern looks like this. So it's maximum in the middle, and it goes down in these waves and has these interference patterns. The reason is that if you scatter from some point in the middle or some point at the edge of the particle, then the length that the wave travels from this point to the detector is different. And therefore, you can have a phase difference, which then leads to some interference effect. And different shapes will cause different interference patterns. So if you go from a sphere to a cube, well, you can sort of resemble the symmetry of the cube. And now you have this square regular pattern of scattering. If you then go to a block where this is now twice as long, you see that this resembles that of a cube, but the vertical axis is reduced. The interference repeats itself more often. So that indicates that if you have longer intensities, then you have shorter frequencies and therefore shorter scattering angles. Now, this can be used to build a model and to interpret your data. So to illustrate a bit, if we take the example of the sphere, if we do the radial average of this, then we see that we have this interference pattern, which has these points where the interference dies out completely, so that the scattered intensity gets to 0. And so this is the Q vector times the size of the particle. And it bends over at some specific number, which is an indication of the size of the atom, or the size of the scattering pattern, scattering particle. And this is a generic picture that in the combination of Q times R is uniform, which means that if you have bigger particles, the scattering will move to smaller angles. From this pattern, you can maybe estimate the contrast or how many you have of this. But you would also like to have a quick way of estimating what sort of sizes do we have. And one way that one classically does look at this is to do this combination that you multiply with Q squared. And then you see that there's a maximum appearing for some specific value. And that then gives you an estimate of what is the average particle size. Now to get to some example, so a widely studied example for model systems to test the understanding of precipitation is copper in iron. And here we have BCC iron with 1% copper. And the motivation to study this was actually in the context of self-healing at high temperatures. And as a side effect, we also saw a lot of precipitation within the matrix, not only at the open spaces, damage sites. And so that's why we studied this with small angle scattering. So the first step is to illustrate what is now the effect of the magnetic field. So here we have an alloy which is 99% iron and 1% copper. And copper and iron don't want to mix, so you get precipitation of nearly pure copper within an iron matrix. And so if we age the system for a long time at 550 degrees Celsius, then we can get a lot of scattering from copper precipitates in iron. So this was studied at PSI, and there you can measure with neutrons with a sample to detector distance where you can move the detector further away and probe different length regimes. You can see that if you now do not apply a magnetic field, then also the magnetic scattering becomes isotropic. And the message is that if you don't apply a magnetic field, then you cannot properly separate magnetic and nuclear scattering. So if you then do apply a field, which should be at least half a Tesla, but preferentially more than 1 Tesla, then you align the ferromagnetic BCC iron matrix, and you get contrast from the non-magnetic copper particles that are embedded in the matrix. And you clearly see this sort of 8-shaped scattering pattern that is originating from the magnetic scattering, as the magnetic scattering is absent along the magnetic field and maximum perpendicular to this field. So because you know that the nuclear scattering is isotropic and the magnetic scattering is anisotropic, you can now separate the two and learn something. So to illustrate, if you do not apply a magnetic field, what happens is that you get magnetic domains, which are about half a micron. And this scattering from those variations in orientation completely dominate the signal. So if you do not apply a magnetic field, essentially you cannot study your precipitates because the signal will completely only probe the magnetic domain size, and then you don't learn the thing you want to learn. So for materials that have a magnetic matrix, and that is in most of the regular steel samples below 770 degrees Celsius, you will need to apply a sufficiently large magnetic field in order to saturate magnetically the matrix and then study the non-magnetic inclusions within the magnetic matrix. And then you get access to the particle sizes which are in the nanometer range. So if we go to the iron copper system, so if we don't do any deformation, then there are different samples. We have samples where we have not deformed the sample and aged the samples, and we compare that to samples that were first tensile deformed up to a certain degree of deformation, and then were aged by heating to high temperatures, 550 degrees Celsius for a certain amount of times. This is 12 hours. And you see that you get spherical precipitates inside the matrix. And if you have deformed, you also get all these dislocations, which help you to also get additional precipitation. The precipitate itself, if they're very small, they're coherent. And if they get a bit bigger, then they get these internal structures, which have these zigzag patterns, which are also known as having internal 3R and 9R structures. So now if we look at the scattered intensity, we have here the scattered intensity, which is given in a certain cryptic information, but you only need to know that this is the scattered intensity on a log scale compared to Q, which is essentially proportional to the scattering angle. And the angles that we probe are typically of the order of 1 degree. Yeah, so the midpoint is roughly 1 degree, and it goes to several degrees and a fraction of a degree. So we have two types of scattering: the isotropic scattering from the nuclear contrast, which is chemical in origin, and we have magnetic scattering, which is which originates from the difference in magnetization. And the black is before aging, and the red is after aging. So you really see that there is a big increase in scattering in this range of scattering angles or Q values. And that scattering originates from the precipitates. Now, if we calculate, we can see that the magnetic scattering is about 8 times stronger than the nuclear scattering. And therefore, it's much easier to, in this case, analyze the magnetic scattering rather than the nuclear scattering. If we then apply this trick where we multiply the scattered intensity with Q squared, which we have also done for this theoretical case where we looked at the sphere or what it scatters, then you get these particular patterns. So you see that for short times there's essentially no scattering from the precipitates, and the longer you wait, the more area you get under these curves, which gives an indication that the phase fraction of precipitates increases. And you also see that this maximum moves continuously to lower and lower values. And a lower maximum in Q means a higher size in space, because Q is a spatial frequency and R is the size of the precipitate. We see that there are some differences if you deform or undeform, but these differences are weak for the copper precipitates in iron. So basically, theoretically, we can demonstrate that if we do this integration of what is below this curve, then you get something that is proportional to the phase fraction. So we have fractions of about 1%. So 1 minus this fraction is about 1. And here we have the contrast, and the rest are just constants. So the integral is a direct probe of the phase fraction. So you can see that if you, over time, you continuously get more and more precipitation, and that you get to about 0.5% of copper precipitates in iron matrix. You can also see that initially it goes faster if you have deformed, because there are more nucleation sites, but you end up at lower values because you also start to decorate the dislocations, so there's less copper available to precipitate in spherical particles. Now, if you want to analyze this, you can do this quantitatively in this way. The scattered intensity goes with the contrast term, and there's a size distribution involved. And we can define two different size distributions. One is the number density, and that we typically do in a log normal distribution. So if you integrate this, then you will get the number density of precipitates. And the other way to look at this is to do a volume size distribution. Then you have to multiply the number density by the volume. And if you would integrate this over all the sizes, you will get the phase fraction. Well, here's the form factor that goes into there, as we have seen earlier. So if we now do an actual fit with log normal size distribution, then we see this, that the volume distribution, you see that it initially nucleates at very small sizes, it grows in intensity, and then once it has reached a sizable fraction, um, the average particle size continuously moves up while the phase fraction, the integral, does not grow that much anymore. So the power is that all this is measured in situ at high temperature. So the sample was actually at 550 on the instrument, and we wait, so we have all the time steps in between also. So you can see continuously how it evolves during the precipitation mechanism at high temperature. Now, according to the literature, there are different steps in the precipitates. So we don't really see those in the SONS experiment, but from the literature, we know that the steps that are identified happen at specific sizes. So if we take those as limits for the different types as critical transitions, then you can actually see how these, estimate how these different components evolve during the aging time and as a function of pre-deformation, whether you have applied the tensile deformation or not, and if you have applied different levels of tensile deformation, because they define the dislocation density at the start of the experiment. Now, this is one example for iron copper. You can then also go to particles that are not spherical. So we have looked at gold and iron. So it also segregates in a way where the precipitates are nearly pure gold in iron matrix. And you can actually see that if you do the same type of experiments, that in that case, because iron is so much bigger than that gold is so much bigger than iron, that there's a big strain energy penalty. So if you don't deform, it will be very difficult to nucleate gold. And that's why if you don't deform, then the precipitation is strongly suppressed in this case, while if you start to have a pre-strain in a tensile experiment of 24% strain, then you see that there are lots of these plate-like precipitates, which are very flat, and are all connected to a dislocation. So now we can see what happens then in a case where you have these very flat precipitates that form inside the matrix. A lot of things are the same, but some things are different. So you can now see that if you do not deform your material, or in the initial stage, they all have something that is related to the scattering from grain boundaries. And if you then look at the sample after 12 hours of aging, then you see that if you have not deformed anything, then you have not gotten any extra scattering. So no precipitates are formed. In the TEM, we saw a very small number of those and only at grain boundaries. So if you then deform, then you start to induce the precipitation of these plates, and they all need some dislocation to nucleate. So that's why if you have more deformation, you have more precipitates. Yeah, so in the magnetic scattering, you see something similar, that you have a strong increase in scattering if you have deformed your material. And that's an indication that both from the nuclear and the magnetic scattering, that you do actually need the deformation to induce these plate-like precipitates. So these plates are very anisotropic. So the length is about 10 times the thickness. And that means that you have now two types of characteristic sizes. So we have seen that the scattering is sort of constant below a critical frequency, which is related to the dimension of your sample. But now, because we have two different dimensions, There is also in the intermediate region where it is big for one frequency and small for another frequency. And that's why we now have 3 different regimes with different power loss. And that's also what you see over here, that we now have a different type of behavior in the intermediate range. So you can also obtain the phase fraction in the same way, and you see that there's no precipitation without deformation, and the more deformation you have, the more precipitates you form. So that all makes sense. Well, I will skip this one. So the analysis for anisotropic particles that are randomly distributed in orientation is now a bit different because you need to adopt a certain aspect ratio for 2 sizes, and the scattering pattern is much more complicated, but all that is done in fitting programs which help you to analyze this. So that now allows you to get the particle size distribution also as function of time. I will mainly illustrate that the size distributions you get for the different alloys, one is iron gold and one with added boron and nitrogen, that can be analyzed. You get the sample dimensions over here, and so those are the plate thicknesses, and that can be directly compared to what you have in TEM. But in TEM, it also is a lot of effort because you need to combine a lot of different pictures to obtain a size distribution. But you see that this compares fairly well, as long as you have the right magnification range available in the TEM. So one last example where we added additional tungsten and then did cold rolling rather than tensile deformation. In that case, we see this picture. So we see all these plate-like precipitates, and they actually only occur in 3 different orientations with respect to the BCC iron matrix. So all the plate normals of these gold precipitates are under a line with the principal axis of the BCC cubic lattice. So you have 3 orientations. We see a flat particle, we have a line like this, and we have a line like that. So those match, they line up with the principal axis of the ferrite grain in which these plates are actually formed. Now we also did time-dependent measurements of this, and one complication arose that actually these cold rolled samples have a significant amount of texture. And that means that the scattering pattern is no longer this nice H-shaped particle, but you now need to include what the texture is to be able to analyze your data. Now the advantage here is that we can measure the texture of the BCC iron, and because we know that the plate normals of the gold precipitates line up with the principal axis, you can actually, by studying the texture of the ferrite matrix, say something about the preferred orientation of these plates in the matrix, and then analyze whether that matches the scattering pattern. And that worked actually quite nicely, that you can then explain that this is actually extended more than what you would normally have because you have a dominant population for these orientation. So after this, you can numerically then analyze what the phase fractions do if you do heat treatments at different temperatures, and you can follow the size distributions as a function of time for all these aging steps. And that can be translated in precipitate fractions and sizes. And you clearly see that if you increase the temperature, the precipitation goes faster, but you reach lower equilibrium phase fractions. And that is all in line with what you expect to see. Now, one last topic. If we look at the precipitation in vanadium carbides, in nanosteels, we can also see how the precipitation strengthening takes place. So this is a continuation of the work that Eric Offerman did some years ago. The basic aim is to look into these nanosteels, which have a ferritic matrix without any secondary phases other than the vanadium carbide precipitates. And this should enhance the strength with keeping a high formability with various applications. So there are various ways of making these precipitates. Quite common one is to make interface precipitation, and then you get these nice regular patterns of precipitates within the final matrix. That can also be studied with small angle scattering, TEM, and atom probe, of course. So previous work is listed here. So this is the interface precipitation. So what happens is you austenize, you cool to below the austenite to ferrite transformation, and then at the interface, all these regular precipitates are formed. So in recent times, we wanted to see whether we can adopt other routes and see whether they would be beneficial. So the other route that we now are studying is random precipitation. So what we do is austenitize again, quench to room temperature to make a fully martensitic structure and a lot of dislocations, and then reheat and age to then have a high density of nucleation points and a fast growth of the precipitates. So for the alloys that we studied, so we have two compositions with two different vanadium and carbon contents. Both are doubled for the high carbon, high vanadium, compared to the low carbon, low vanadium samples. If we then again look at the scattered intensity times Q squared versus Q, then we see that the amount of scattering increases as a function of the aging time at 650 degrees, as you would expect for the precipitation, but also that the peak is found at lower Q, which means that it's actually indicates that the scattering comes from growing particles. We also see that the scattering for the high carbon, high vanadium is about twice as that of low carbon, low vanadium. So that also makes sense. The fitted size distribution shows then particles in the range of a few nanometers, and you have an increase and a growth in the particle size as expected. And what we can derive from this is what the phase fraction does if we do the fitting. So we see that it continuously increases, but has not reached the maximum, the equilibrium phase fraction within that 10 hours. We see that the equivalent size, the size of the particles, the average size of the particles does not necessarily depend a lot on these concentrations. And that the density already starts to decrease fairly quickly, but much faster in the end stages. So especially these end stages indicate the coarsening of the precipitates, but the fact that you already at the earlier stages also have a reduction in number density indicates that coarsening is already starting at a very early stage. Now from this, we can recalculate what the expected strengthening is. So here we have one of the models for the precipitation strengthening. So we have the shear modulus and the Burgers factor, but what we have access to is the phase fraction and the radius, and we can plug that in. We get these sort of pictures, so that we have roughly a plateau, and when we get into the coarsening regime, it's starting to go down. And one way to maybe illustrate this further is this picture over here. So if we have a color contour for this precipitation and strengthening equation, the model that we adopt here, then we see that depending on the phase fractions that you can achieve and the sizes, you will have the maximum effect for small sizes and high fractions. And you see that for the contours that we follow in this particular experiment, that we nearly follow a constant value. And that explains why we have this plateau in the strengthening. And only if we would reach values that are close to the equilibrium with a further coarsening, you will have a continuous reduction at later times. So this is very illustrative. Depending on the different processing routes that you adopt, you can monitor as function of time how you go through these profiles. So that concludes what I wanted to say. Here are a lot of people that have been involved in the things I have discussed. And the last picture over here is at ISIS, where we have worked together with Stephen Parnell. And most of the recent work is from Zamron Khan, who is here in the middle.
Okay. Thank you, Erik. Thank you for a very comprehensive and nice presentation. So, which is now open for discussion, but let me first stop the recording. Okay. Yeah. I want to stop.